In this first video, we're going to look at how to parametrize surfaces. Let's just take one quick step back and understand how to parametrize uh, curves. Right, so to understand the parametrization of surfaces, let us first quickly review okay, the parametrization of curves. So what are curves? All right, curves are essentially one-dimensional shapes in multiple dimensions. So, for example, a curve can sit in 2D, right? Here's a curve. It has a starting point and an ending point. The starting point and the ending point may be the same. Or in 3 dimensions, I might have a curve that looks like this, and it could stop, right? It might have a beginning point and an ending point, or it can go infinitely in both directions. That's also possible. So examples of parametrizations for curves, let's give some examples. For example, let's do this one, C from 0 to 2 pi to R2, given by C of t equals cosine of t sine of t. So basically what this traces out is the curve given by a circle of radius 1. So here's a circle of radius 1. And um, and each point of the domain, here's my domain, gives a point on here. So here's C of 0. C of 0 is 1 comma 0. Here's C of pi over 4, which is root 2 over 2 comma root 2 over 2. Here's C of pi over 2, which is given by 0 comma 1. And here, for example, right, C of pi is negative 1. And as the time parameter, so here, this t is called a parameter, okay, goes from 0 to 2 pi, then the curve traces out a closed circle of radius 1. Here is another example. Say C goes from R to R3, given by C of t equals 1, 2, 3, plus t times 1, 0, 1. And you can also write this as t plus 1, 2, and then 3 plus t plus 3. So in this case, we have a 3-dimensional setting. Here's the x-axis, y-axis, and the z-axis. This curve has the point 1, 2, 3, say right here, 1, 2, 3. And then there's a vector, 1, 0, 1. And what that happens is that as you increase t, you increase this vectorial piece. And so you get a curve, maybe do it in blue, you get a curve that moves like this. This is not really drawn terribly well to scale. So when t is equal to 0, I'm right here. So here's C of 0 equals 1, 2, 3. C of 1 right here is equal to 2, 2, 4. And then it also goes backwards. C of minus 1 is equal to 0, 2, 2. Again, very badly drawn to scale, but you see here that, there's an arrow. The arrow should actually technically go in the direction where t is increasing. So we can draw an arrow like this. All curves should have an arrow attached. So, for example, in the previous examples, like I should have a little arrow. going here, indicating what direction we're headed. So just as curves can be parametrized by one parameter. We saw the parameter earlier was t. Surfaces can be parametrized by two parameters. And the parameters have different manifestations depending on the problem. You can have parameters in U and V. You might see them in S and T. When you have circular objects, R and theta. When you have spherical objects, you might have theta and phi. It really all depends on the situation, right? So surfaces can look like they can be flat, meaning that it can just lie on the xy plane. So here's an example of a surface just lying in xy plane. Or it could lie in multiple dimensions greater than 2, say 3 dimensions. It could look like, a bent surface like this. It could look like a paraboloid like that. It could also look like, for example, a cylinder, right? Anything with a two-dimensional outline to it is going to be a surface. And so now we're going to look at lots of examples on how surfaces are constructed. Now let's start taking a few examples of how we go about parametrizing surfaces. And we'll do some examples, and then we'll talk about sort of some technicalities and exactly what we're doing. Suppose we wanted to take a plane, consider a plane, say z equals 4x plus 3y. Then we can consider a parametrization of the plane in the following way. We take t, which will be the definition of the function related to the parametrization, just like C was above for curves. And then we can take the entire real plane, and then we can put that into R3. And then we can either do one of two things. We can say t of xy is equal to, and here I need 3 coordinates, so x, y, and then the z coordinate is 4x plus 3y. Another way we can do it is just not to confuse the x's and the y's and just use a different set of letters, uv, which I kind of prefer, uv 4u plus 3v. So this would be our parametrization of the entire plane. Now, what if you only wanted part of the plane? Okay. What if you wanted only part of the plane? So for example, say I have a plane. Here's my plane, okay, right? But I'm only interested in, say, the plane that's above this little rectangle right here. So say that's A, that's B, and that's C, and that's D. Say this is the x-axis right here. This is the y-axis right here. And what I'm really interested in is not the entire plane, but just the part of the plane that's above this rectangle. So if you can imagine drawing little vertical line segments up here, and then you're only interested in this piece right here. Okay, that's an example of a curved surface. It's tilted. So suppose, okay, we want, let's just give a different example, to parametrize the plane, say z equals 3x minus 2y plus 7 above the rectangle AB cross CD. This notation right here means the rectangle with x coordinates A to B and then y coordinates C to D. Then we would write T from AB to CD, right, going from to R3, given by T of UV is equal to U comma V comma Z. The Z coordinate is 3U minus 2V plus 7. Another way that you can write this would be the following. Just write TUV equals UV 3U minus 2V plus 7, and then tell us where the coordinates of U and V are going to range between. So you can do that. Alternatively, you can also write U as an element of AB and V as an element of CD. So either of these possibilities is okay. Let's do another example. Let's take a paraboloid. So a paraboloid, what does a paraboloid look like? Z equals, say, x squared plus y squared. What this looks like is, in 3 dimensions, a paraboloid looks like this, right? It's infinitely large. It just keeps going up and up and up. And so to parametrize the entire paraboloid, one can write T of UV is equal to UV, and then my Z value is U squared plus V squared. And you can write U is between minus infinity to infinity, and V is also from infinity to negative infinity to infinity. That's one way that you can write it. Another way to write it is that T is a map from R2 to R3, given by T of UV equals UV U squared plus V squared. Now, suppose we were interested in just a segment. Suppose we are interested in simply a piece of this paraboloid. So here's an example. Suppose we were interested in the paraboloid, but we're only interested in the paraboloid above, say, a square. Say I have a square. Okay, so say the piece of the paraboloid above, say, -1, 1 cross -1, 1. So what would that look like? So I have a paraboloid, and the piece above the square looks a little bit funny, right? So it looks like it doesn't quite look. It has like these sharp edges, and then it goes up like this. It goes like this, right? So it's not circular on the top. It has these corners. So that would be what the paraboloid looks like above this little piece right here. And so what if you were interested in parametrizing this set? Then I would write t from -1 to 1 cross -1 to 1 to R3, given by t of uv, same parametrization, just different domain, u squared plus v squared. Or you can write t of uv equals uv u squared plus v squared, and specify that u is between -1 and 1, and v is between -1 and 1. Now, this is kind of an unnatural shape. So what if you wanted to do something slightly different with my paraboloid? Suppose we want to parametrize the part of the paraboloid z equals x squared plus y squared, c equals, say, 4. So let's see what this looks like. I have a paraboloid, but I'm cutting the paraboloid off in the plane z equals 4. Now, if you take a look at the intersection between the two, intersection of the two spaces, the two objects, one's the plane and one is the paraboloid, I get z equals x squared plus y squared and z equals 4. If I set those equal to each other, I get x squared plus y squared equals 4. That means that this circle right here has radius 2. Okay. This is a circle of radius 2. Now, what you want to do in this situation is that you want to imagine that you're casting a shadow. So this blue circle right here, imagine that you're casting a shadow, and this becomes this circle down here onto the xy plane. And so what happens is that instead of a square, like we had up here, we actually have a circular domain. And circular domains are rendered by polar coordinates. So in this case, to parametrize this shape right here, right? Now, again, the shape is a bowl. It doesn't have these corners. It has a perfect circular top, okay? So it looks like this. It doesn't look like the spiky cornered ones that we had above. We have to talk about polar coordinates. So here, so x, we're going to call r cosine theta, and y is r sine theta. Then z is equal to x squared plus y squared. So that's equal to r squared cosine squared theta plus r squared sine squared theta. And then I could factor out the r squared. I have cosine squared theta plus sine squared theta. So z is just simply r squared. So in this case right here, we can write t, but t is in terms of r theta. X is r cosine theta. Y is equal to r sine theta. And z is equal to r squared. And what exactly do we have going on here? R is going from 0 to 2 because the radius is 2, and theta is going from 0 into 2 pi. So this guy is the parametrization for this bowl. Or you can write t is a function from 0, 2 cross 0 to pi, into R3 given by T of R theta equals R cosine theta, R sine theta, R squared. So you see that there are two different kinds of ways of, taking slices of surfaces, pieces of surfaces, depending on what kind of piece you want to look at. All right. Let's do another example. Let's take a cone. Consider a cone given by z equals square root of x squared plus y squared. Underneath, say z equals 5. In this case, I have a cone. It looks like this. And then it is cut off above by z equals 5. Now, let's set the two equal to each other. So I have square root of x squared plus y squared equals 5. So x squared plus y squared equals 25. So this is a circle of radius 5. Now, so where is the circle of radius 5? It's right here. The circle, this blue circle right here, circle of radius 5. I'm going to project it down here to the xy plane. And then I'm going to do my parametrization. The parametrization of this cone, of this finite height cone, is given by x equals r cosine theta, y equals r sine theta. And then z is the square root of x squared plus y squared, which is you can calculate that out. It's the square root of r squared, which is r. And where here I have t of r theta equals the x coordinate, the y coordinate, and the z coordinate. And the r goes from 0 to 5, and theta goes from 0 to 2 pi. And again, just to be precise, another way of writing this, 0, 5, 0, 2 pi to r3 is given by t of r theta equals r cosine theta, r sine theta, comma r. Now, there are many, many different kinds of surfaces. Okay, one of the advantages of using parametrizations is that you can use it for both so-called functions and non-functions. Is that it can be used to describe functions and non-functions. So what do I mean by that? In the examples that we've seen so far, okay, these are functions of z. Like we've seen something like z is a plane, z is a paraboloid, z is a cone. In all of these cases, you basically have something that looks like that, more generally, and it passes the vertical line test, right? So every vertical line will hit the curve at most one point. But you can also have non-functions of z. So for example, if I have x squared plus y squared plus z squared equals 4, this is a sphere of radius 2. Now, the thing about a sphere of radius 2 is that it does not satisfy the vertical line test because it actually hits the sphere in two places. But it turns out that it's still a surface, and you can still describe it in a parametric way. So we're going to be talking about that in just a moment, right? So let's talk about cylinders. All right, so let's actually call this A and B, and then we're on example 4. Suppose I have a cylinder. Consider a cylinder given by, say, y squared plus z squared equals 9, and x is between 0 and 3. Now, notice right here that this turns out to be a little bit more challenging to draw. I mean, it's not so bad. But if this is x and here's y and here's z, then we have a cylinder which is of radius 3 in the yz plane, and then the axis is on the x-axis. So here's 0, here's 3, and here is my cylinder, and it looks like this. So in this case right here, okay, notice that we actually only have, the radius is always 3, okay? So here, the radius is always 3. So basically what happens here is that y and z represent the circular pieces. It's always going to be 3 cosine theta and 3 sine theta. And then x is just x. Right? So you can write this parametrization as x theta, and then the x is just going to be x. The y is 3 cosine theta. The z is 3 sine theta. And x goes from 0 to 3, and theta goes from 0 to 2 pi. If you don't want to repeat the use of x, you can always write t of u theta. That's also okay. U, 3 cosine theta, 3 sine theta. And the other way to write it, of course, is t goes from 0 to, 0, yeah, 0, 3 cross 0 to pi to R3, given by t of u theta equals u 3 cosine theta, 3 sine theta. Let's tackle the problem of a sphere. Sphere is complicated. Okay. A sphere, x squared plus y squared plus z squared equals a squared. Well, let's think about it for a moment. Recall spherical coordinates. Spherical coordinate says that to parametrize or to describe a solid ball, say x squared plus y squared plus z squared is less than or equal to a squared. So the solid ball looks like this, and it has the entirety of the inside. The radius is a. Then the description of spherical coordinates is x equals rho cosine theta sine phi, y equals rho sine phi, theta sine phi, and z equals rho cosine phi, where rho is the distance from the origin to your point. That's rho. Theta is the angle from the x-axis right here. And then phi is the angle that you drop from the z-axis. That's phi right there. Okay, so let me just draw this a little bit more clearly, right? If I have a point in the ball, then I have an angle phi, I have an angle theta, and then I have a distance rho. And here, rho goes between 0 and a, theta goes from 0 to 2 pi, and phi goes from 0, which is the North Pole, down to the South Pole. Now, if I'm not interested in the solid ball, right here, we're just looking at a sphere, which is just the shell, right? The sphere is the shell or the boundary of the ball. Okay, then rho is always a, this a right here. So we would just need x to be a cosine theta sine phi. Y is a sine theta sine phi. And z equals a cosine phi. And here, notice that we only have two parameters. Theta goes from 0 to 2 pi, and then phi goes from 0 to pi. So here I can write t of theta phi equals a cosine theta sine phi, a sine theta sine phi, a cosine phi, where theta goes from 0 to 2 pi, and phi goes from 0 to pi. Of course, the other way of writing this is that t goes from 0 to pi cross 0 pi, and it goes to R3, given by t of theta phi. Exactly the same formula as above, but just sort of written slightly differently. It looks like this. Let's talk about now an ellipsoid. Ellipsoid is very, very similar to a sphere. Ellipsoid looks like x squared over a squared plus y squared over b squared plus z squared over c squared is equal to 1. So the parametrization is similar. So x, you're going to say is a cosine theta sine phi, y is equal to b sine theta sine phi, and z equals c cosine phi, where theta goes from 0 to 2 pi, and phi goes from 0 to pi. One very interesting object is called the helicoid. So let's just remember that there's this object called a helix, a curve given by the following. Say c goes from 0 to 2 pi to R3, c of t equals, say, cosine t, sine t, t is a helix. So what does this look like? The idea here is that I have x and y going in a circle, but as I'm going in a circle, the z coordinate is actually increasing. So it looks like this. Okay, it's a circle, but it's strung out like a slinky. And this is called a helix. If I increase the domain, then the helix keeps going up like this. Now, a helicoid is a version of the helix, except that what you're going to do is you're going to fill in this thing right here so it looks like a slide. Okay. So a helicoid has sort of a boundary that looks like a helix, but the interior is attached to the z-axis. And so a helicoid looks like the following. Okay? The parametrization of a helicoid is t r theta. This is r cosine theta, r sine theta, and then just plain old theta. And r, say it goes from 0 to 1, and theta goes from 0 to 2 pi. Now notice that this is the first example that we've had of a surface that is defined by a parametrization directly. So what do I mean by that? Before, right? So before, we always had an equation to start with, like z equals x squared plus y squared, or x squared plus y squared plus z squared equals a squared, and then we transformed it into a parametrization. Here, the helicoid, it's actually very, very difficult to write a helicoid in terms of something like this. And so we just directly define it by the parametrization without first going from some closed formula. Now, there are a few things that we need to talk about insofar as what the picture kind of looks like, right? What is sort of the transformational picture here? Okay. So suppose we're looking at suppose we are looking at our previous example, say z equals x squared plus y squared, the paraboloid, okay, underneath z equals 4. So again, what we have here is we have a paraboloid, okay, and it's being cut off at z equals 4. And the parametrization would be x equals r cosine theta, y equals r sine theta, and z is r squared cosine squared theta plus r squared sine squared theta. And that's equal to r squared. Here, if you look at the intersection, it's x squared plus y squared equals 4. So this is a circle of radius 2. So that means that r goes from 0 to 2, and theta goes from 0 to 2 pi. Now, when we write t of r theta is equal to r cosine theta, r sine theta, comma r squared, with r going from 0 to 2 and theta going from 0 to 2 pi. Okay. And again, remember that we have a different way of writing this, which is 0, 2 cross 0, 2 pi to R3, given by t of R theta is R cos theta, R sine theta, R squared. Effectively, what we're doing is the following. We're taking this domain. What does this domain look like? Well, we're the R theta coordinate system. It's a little bit weird to think of R theta as being coordinates. You usually think of X and Y. But here, the first coordinate is R, the second coordinate is theta. You're taking R goes from 0 to 2, and theta is going from 0 to 2 pi. So what you're doing is you're taking this rectangle in R theta space, and you're going to take that via t, and you're going to bend it into a paraboloid that looks like this. Right? So the way to interpret a parameterization, in a lot of cases, not all cases, is that you're really taking, in many cases, let me write this down, in many cases, a parametrization, okay, is a map from a rectangle to a two-dimensional curved surface in three-dimensional space. I mean, as another example is the issue of a sphere, right? A sphere x squared plus y squared plus z squared equals a squared. What you're effectively doing is you're taking theta phi space. Theta goes from 0 to 2 pi. Phi goes from 0 to pi. So you have yourself a rectangle in theta phi space. And then you are applying t to it. And you're taking the rectangle here, and you're basically bending the rectangle and making a sphere out of this. This is the way that one can think of these kinds of parametrizations transformationally, taking a rectangular space, not in all cases, right? We'll see in other videos. So we will have some supplementary videos. The supplementary videos will look at more examples, and it'll study non-rectangular domains, and a lot of other interesting shapes that we can study other than the ones that we've seen so far. So this is the end of this video. The next video in the series will be about surface area, okay, which is the analog of arc length. Arc length in curves, we can find surface areas of surfaces, and this will involve some integration, and we will derive that next time.